in the first equation, we have an x minus 2 times negative 1 plus 3 times 2 equals 9. And x is equal to 1. How do you think you write your answer? Yeah, your answer, instead of it being an ordered pair, because an ordered pair is x comma y, this is called an ordered triple. There are now 3 variables, and the solution to the 3 variables is still where these intersect. Now, once you throw a third variable in, you're in a third dimension. So this is like a 3-dimensional graph. So you have your x-axis, you got your y-axis. The z kind of goes through, and it makes it a 3-dimensional graph. But they still all intersect at this one point at 1, negative 1, and 2. So your solution is an ordered triple. This does ask you to check your solution, and you will be asked to check your solution. So to check it, you just have to make sure it works in every problem. So if I plug in a 1, a negative 1, and a 2, that better equal 9. So again, you will be asked to check your solution to make sure it works. So everybody should know that their answer they found was correct or incorrect without even checking the back of the book, just because you checked it into the original problem. So this makes 1 plus 2 plus 6, which is 9. So that one's good. When you check your solution, you got to check it into the next one as well, because it could work for one and not the next. So if we plug in negative 1 plus 3 times 2, that also makes 5. So that one works as well. So checking it into both or all 3, depending on how many equations you have. The last one's just equals 2, so I mean, obviously 2 is 2. Don't really have to check that one. So ordered triples, don't just leave them hanging out by themselves. They represent a point where these 3 lines are connected. So today we are going to look at equations that are in this form. So this form where you have 3 variables and then 2 variables and then a single variable by itself is called row echelon form. So they're in 3 rows, but each row has 1 less variable as you work down the problem. We call it like a stair-step pattern. So you have 3, like you're going down the stairs, kind of working yourself down. Thanks. So we are going to try and take equations that aren't in this stair-step pattern, and we're going to try and get them there. So if you look at the example underneath, notice that you have 3 variables. We have an x, y, and z. In the next one, we have an x and a y. There could be a z there. And then we have an x, y, and a z again. So our goal is to take an equation that looks like this and to try and get it in that row echelon form where we have 3 and then 2, and then the last one would be a single variable by itself. The gentleman who created this process is called Karl Gauss. It's actually Carl Friedrich Gauss. But he found a way, using elimination, to systematically work through problems with multiple variables to try and help you eliminate a term or a variable from the problem so that we can get it into this row echelon form. It does say there are many ways to do this. Of course, with math, I mean, there's one right answer, but as we saw in the trig and those identities, there are many ways to get to that one right answer. So the book suggests leaving the x's in the upper left corner and eliminating the x's in the first column. And that's what we're going to look at. So our goal is to literally get it to look like this, where you have an x, but then no x's underneath it, because that's true row echelon form. And then we have the y's, but then again, like no y underneath, so that we have this pattern where we're losing a variable each time. So to do that, we're going to use elimination in a slightly different way. And if you start just with the first 2 equations, so when you use elimination, you can't use all 3 at the same time. It's still just 2 equations together at once. So we're going to take these 2 equations, the first 2. We're just going to kind of pull them off to the side. So I'm pulling these 2 equations off here to the side. what would eliminate with these equations really easily, Colin? The x's. So if you took these two equations and just used regular elimination, put a plus sign here, and combine them together. What do you get, Colin, when you combine those together?
You get y, 1y plus 3z equals 5. Right.
There's really just a big 0 here with the z, so you're just adding 3z to 0, and then that's equal to 5. This is called your resulting equation. We eliminated a variable, but we didn't eliminate two. But at least we have one less than what we started with. So looking at the first equation with what we started with, we have x minus 2y plus 3z equals 9. I'm not going to write this second equation, but instead I'm going to use its result by combining those two together and writing the y plus 3z equals 5 underneath it. So it's a resulting equation. It's what we found by taking two and combining them together. This now has a stair step. So I have 3 variables, and now I have 2. And if you look at the problem above, we had 3 variables, and then we had 2. So our goal is to continue this process because we want to have a third variable for z by itself. But you can't get that right away. You got to do a couple of other steps. So if we use the first two equations and squish them together and got a resulting equation. If you go back to the first equation and now look at the third equation, we're going to try and do the same thing. So we're going to take equation 1. We already used equation 2, so we're done. We got a new equation to represent it. But if we go back to the first equation and look at the third, because our goal is to get like a third equation underneath here. How could you use elimination with equation 1 and equation 3? So think of this as like 1, 2, 3. We used 2. We're going to go back and try and think of how we could eliminate 1. What could we do to get that second or the third equation eliminating just the x term? Colin? Yeah, so if we take this top equation and multiply by -2. So again, we're eliminating x. Our goal is to get the x's out of that first column. So thinking about all of the x's in a column, all of the y's, all of the z's. So we're trying to eliminate x from everything in this problem except that first equation. First equation gets to keep it, it gets to stay the same. So if you multiply by -2, Josh, what's that first equation become?
Negative 2x plus 4y minus 6z.
Oops, yep, you're right. And that's equal to? Negative 18. All right, so here's our third equation underneath it. 2x minus 5y plus 5z equals 17. And if you add them together, what's your resulting equation? God bless you. Colin, what do you get?
You get negative y.
God bless you.
Minus z equals negative 35.
Equals.
Oh, never mind. It's negative 1.
So you said negative y minus z equals?
It would just be
negative 1. So if I take this resulting equation and that resulting equation and combine them together, what's going to happen? The y's will cancel. Remember, our goal is to have 3, 2, and then just the z by itself. So if you take these two new equations, we're going to use those two new equations and combine them together because they both have a y and a z in them. So we used elimination. We eliminated x's. Our resulting equations both have the same variables. So we have a y plus a 3z equals 5. We have a negative y minus a z equals negative 1. So that's our result. That's what we got when we took 1 and 2 and added them together. And then we took 1 and 3 and added them together. So Emma G, what do you get when you add these together? 2z equals and then z is equal to. So now if I go back into this, we end up with z equals 2. Yeah, crazy, right? So we used elimination 3 times. You have 3 variables. The first thing we did was we took equation 1 and just added it with equation 2. The goal is to eliminate x underneath that first row. So the first row is never going to change. It's going to stay the same. It's a big expanded form. So by adding the first 2 together, we get this new result, new equation. That was created from combining 1 and 2. We're done with that second equation. Now we need to think about how can we add another group or another pair together, 1 with 3, so that again, we get a new result. If we eliminate the same variable from both of them, then I have 2 variables left that are also the same. Question?
So, for example, if there was a problem with the second equation was on top, where like the number 1 would be, could you move them around?
Sure, you can.
You can do that to
Yep.
like make all 3 variables on the top row.
Yes, yes. Yes, so good question. So I would suggest if you don't have, he said, what happens if this equation would be on the top? You're allowed to like maneuver, rewrite the equation so that you have all 3 on the top row to use then to kind of work with. Obviously, we're going to try it again. Okay, 1 example would be enough because this is totally new. Yeah. So we're going to do another one. It is a long process. We use substitution or elimination 3 times, and you're going to have to use elimination multiple times. We did not finish solving this. Does anybody know why we didn't finish solving it?
Because we define x or
It's the same, thank you, Garrett. So the reason I didn't finish solving this problem, it now is identical to the first one. So that's why I figured we didn't need to solve it. But maybe you want to write the solution since I kind of skipped over that part. So now that we know we have that same equation, same set of equations that we had on top, the solution is 1, -1, and 2. But just to show you that, I mean, it didn't look the same, but by doing this elimination process, it did become exactly the same. All right, so let's look at example 2. We're going to keep that first row the same. You're going to use the first row to eliminate the x underneath it. And again, you can only do 2 at a time. So Lauren, what would you do with the first equation so that we can eliminate the 2x in the second equation? Yeah, so we're going to take this, multiply it by -2. And then the second equation we're not doing anything with, just keeping it as a 2x minus y minus 2z equals 2. So elimination, you multiply by something, the goal is to eliminate a variable. Lauren, when you add them together, what do you get? Yeah. So first equation staying the same. Now I have a stair step starting because my second equation now has 1 less variable. We got rid of that x. So you can see that stair step happening. So done with this second equation, it's gone because now there's a new equation that represents it. They're equivalent because I still kind of added things in the problem together. All right, so going back to equation 1. And now trying to look at equation 3. Carrie, what could we do with equations 1 and 3 to help us eliminate the x underneath? Yeah, multiply the first one by -1. Or you can multiply the bottom one by -1. It's totally up to you. So the first equation multiplied by -1. The second equation just staying the same. Carrie, what do you get when you combine them together? Equals -2. resulting equation when we combined 1 and 2. Resulting equation when we combined 1 with 3. What would you do next? Now that you have these two equations, what do you do next, Colin?
Use the first equation that you found.
So use that first result. All right, and then what?
Then you take what you found or just found to get rid of the y.
Right, take what you just found, try and get rid of the y's, and we can multiply this by a -1. So we're taking the two results, the two new equations. They're new, we just created them. Combining them together because they both have a y and a z. And when you combine them together, what do you get? 0 equals 2. What the heck does that mean?
No solution.
No solution.
No way.
So I can't find a z because there is no solution to the problem.
Are you kidding me?
What types of lines usually have no solutions? Parallel. So in this case, we have like 3 lines now, but they're in different planes. So this is multi-dimensional. Calc 3 is called multivariable, multi-dimensional calculus. We don't offer that here. You'd take that in college if you're a math science major. But in the book, it has a nice little diagram showing you that these really don't intersect. So you kind of have like 3 lines that are just like stacked on top of each other, parallel with each other. They become planes. Remember, a plane is like a surface. We graph things on just like a regular plane, a regular piece of paper. So we've got 3 of them. Any questions? How do you feel like after you did 2? A little better. Okay.
I feel the last one.
All right, so there's another one underneath. This one's nice. You have X, Y, and Z. This one doesn't have an X underneath it.
So we don't have
So it's like, that's like a bonus.
Oh, okay.
Yeah,
Okay, thanks.
that actually is kind of nice. You were just given a bonus. You don't have to do anything with this row. Leave it be, because your goal is to have 3 variables and then 2. Well, you have 2. But we still need to work with that third one. So the third one has an X. We got to get rid of that X that's in that third equation. So go back to the first. And combine it with the third. And Josh, what do you get?
You get 3y minus 3z equals 0.
Good. So we're done with this third equation.
Check.
It's gone. If you look at equation 2, there's only a y and a z. The new equation that we created also has a y and a z.
No.
So how can we use those 2 equations in elimination? Oh, this is not 3, this is just a z, my fault.
Again, multiply by -3 on the bottom.
Yeah, multiply by -3 on the bottom. So taking this equation, multiplying by -3, gives us -3y plus 3z equals 0. Now we have 0 equals 0. So this means there are infinite solutions.
I'm a genius.
All right. So when there are infinite solutions, in 2 equations, it means they're the same line. If I have 2 equations, it means you have one line graphed on top of the other. And whatever that line would be in y equals mx plus b form is where all the solutions exist. Only on that line. So yes, there are infinite solutions, but you can't just pick any random number. It has to be a number that is on the line. It can't just be any other place. So when there are infinite solutions with 2 lines, if your line was y equals 5x minus 3, that's where your solutions would exist, any point on the line. When you have 3 that you're graphing in an x, y, z format, Yes, there are infinite solutions, but those infinite solutions have to be in a specific pattern. So again, you can't just be like, hey, 1, 2, 3 must be a solution because it says infinite. So we have to write a pattern to represent how the infinite solutions could work. And this is where it gets a little weird. The third variable that we usually get by itself, so if I look up above here, our goal is to get z by itself. In the problem before, again, our goal was to solve for v, for z, not v. Like we're trying to get that one by itself. In order of hierarchy, the x is most important, and then the y, and then poor old z. He's the least important variable. But he actually gets a little bit of love right now because he's going to kind of control the answers. So we're going to take that third variable, and we're going to try and write a pattern using the third variable. When we write patterns, we're going to introduce a dummy variable. So we're going to say, let's let z be equal to the variable a. A is a constant. It represents any number. So we're going to say a equals z. Z is allowed to be any number. Z is then going to affect what y looks like. And then those two are going to affect what x looks like. So if you go to this equation that says y minus z equals 0, our goal is to figure out an ordered triple. So what would x, y, and z look like? What should my solution look like? If z is equal to a, and I want to represent y in a certain way. So we're still trying to get x, comma, y, comma, z. But now we know z is a, because we said it was. This equation would then say y minus a is equal to 0. I'm plugging the z value in of a up here, any number. So that means y is also equal to a. What does that tell you about y and z? They have to be the same. So they can both be 2, they can both be 5, they can both be 7, but they can't be different numbers. So y and z have to be the same. How could I find a way to represent x, Colin?
You plug in a for y and z.
Yeah, so if you plug in a for y and z, and you can go back up to the top if you want. So it says x plus y, well y is now a, minus 3z, well z is now a, is equal to negative 1. Carry x would be equal to 2a minus 1. So now your ordered triple, it can't be any random numbers that you feel like picking. But if you pick a value, maybe a 2, then you could have an ordered triple that works. So if I say a is 2, then my z is 2, my y is 2, and if I plug 2 in for x, then I know my y is 2 times 2 minus 1 is 3. So 3, 2, 2 could be a triple that would work. These are the ones that are more challenging. So you can't just be done and say, oh, infinite solutions, done with the problem.
Done.
So start with z and always start with z. That's the last, like the actual variable that we solve for. So it never has any power except now we're trying to write a solution. So we are going to do the next problem at the top of the next page, and I do want you to get out your calculator. Because I want to show you how you can check your solutions, not only just by hand, but I want to remind you how these solutions can be verified with your calculator. So if you flip the page, this says solve the system using matrices, and then it says check your solution.
I remember this.
So this equation is the same equation right here. It's the same set. So our system is the same set. We've solved this system the first time, we already knew what z was. The second time we solved it using this Gaussian elimination. And now we're going to take this same system and solve it one more time, but we're going to solve using your calculator. Does anybody remember how to set up a matrix for a system of equations? Not even using the calculator. How would you set it up? Hannah. So the first one is called the coefficient matrix in front of each of your variables. You're taking the coefficients of x, the coefficients of y, the coefficients of z, and writing them vertically. So all of your x's should be down the first column. So there's a 1, a -1, and a 2. A -2, a 3, and a -5. And then we have a 3. There's no z, so there's a 0. And then we have a 5. So that's called the coefficient matrix. Again, the x's, y's, z's go vertically. Next to that is your solution set, your solution matrix. Actually, no, let's put the variables here. My fault. The variables we're solving for are x, y, and z. It's equal to the solutions on the other side, or our constant numbers on the other side. And those would be a 9, a -4, and a 17. When you plug this in your calculator, we're taking the inverse of A, that's this guy here. We're multiplying that with B, which is this guy. And that would then equal the x, the y, the z. You need to take the inverse to solve, because technically we're kind of like dividing to get the variables by itself, and the way we divide a matrix is by taking the inverse of it. That was from last year, way back at the beginning of chapter 3. So in your calculator, you're going to hit second x -1. That's where your matrix is. Second x -1. My calculator crashes my computer every time, so I'm not going to pull my notes. I don't want it to crash. So second x -1. What are the dimensions of that first matrix? 3 by 3. After you hit 3 by 3, the dimensions, you should have a 3 by 3 matrix up here. Enter in those values. And then you need to do second quit. Go back into your second matrix. The dimensions are 3 by 1 for your second matrix. So you have to go down to B and then hit edit. Somebody gotta go to edit. 3 by 1 for the second matrix. After you have them in your calculator, you need to go back to the matrix and just pull in the A variable, take it to the -1, and then multiply it by the B matrix. You should get 1, -1, and 2.
Period.
Anybody need help? I apologize for mine not working. It's frustrating. So you should have a 1, -1, 2.
Alright, maybe.
So you have 5 questions, 5 problems. Please show work. Where is your book right now? At home. If it isn't at home, take it home. I don't have worksheets. I got books for some of the problems over the next couple of days. That's why I'm saying take your books home.
See you in April. Happy Easter.
I know why she's. I just thought she was like, it's like.
Well, guys, it's Corona time. Have a good day, Miss Karen.
Thanks, you too. Yes.
Is that